Good morning. So, let me continue with field investigation and that too by direct field investigation. Direct field testing, and I have just discussed about the SPT test. What is SPT test, how to utilize it, and then if I carry out test in the field, whether we can directly use in the calculation or you have to do something. So, I have mentioned that there are some corrections, and most important correction perhaps is the overburden correction, and how to apply overburden correction, that also I have shown that through application. Now, I will discuss about some other technique so that is actually your cone penetration test. This is becoming popular now actually in our country. Still it is not that popular, but it is still it is coming because of many foreign consultant here doing a lot of work. So, because of that this also is becoming popular, and this is a comparatively new method and good for developing profile, continuous profile. That means, you are when you are doing SPT, actually suppose if there is a soil mark and SPT actually over depth, you do 1.5 meter or 3 meter or 4.5 like that discrete. We are getting data at this point, at this point, at this point. Whereas, cone penetration test continuously you will get some profile like this. So, each and every point whatever resistance is getting directly you are recording. So, continuous resistance profile will get, and that will be correlated to different soil properties and all that is there, and it is very fast and less expensive and than drilling an SPT. When that means, SPT actually main part is you have to first of all you have to make a borehole, and then at different different depth you have to conduct test and then go beyond like that. But here there is no point of making borehole, you have to continually push the cone. So, that is why it is faster and is also economic, and it can be used in conjunction with SPT. SPT wherever SPT is done, the SPT can be done also this, and measures friction and cohesion separately can be made, and sometime by using piezo cone. So, you can pore pressure you can measure, you can shear wave velocity also you can measure. So, there are so many advancement in this, but we have very little information. So, information is there, but I do not want to burden you by giving too much of this. So, just minimum I just mentioned here that typically a cone penetration instrument looks like main part of this is this one. They have this dimension actually, this is the one, and when it is collapsed that it can be extended. So, this becomes the dimension, different parts, dimension of different parts are shown here. So, through this actually when you are pushing, there will be arrangement for recording the value, friction value and resistance values. So, that will be I will show you the next slide, and you can see that this is the one, this is the way actually we get the resistance, actually cone resistance QC, that is total resistance over depth. So, 0 to 50 meter the profile resistance profile is given, and friction resistance if it is separated, then over depth same, over depth 0 to 50 meter, this is the distribution we get. And here actually another can be separated Fs by QC in percent, actually that also can be obtained. So, this is the way actually CPT data we get, and once you get the data and you can see this is the variation. So, it is continuously variation, then how to find out every point the different soil will be treated like that? No, actually I can see that this is the average value. So, up to this there is a one layer, and you can see up this is the layer, this must be the another layer. So, again from here there may be continuous changes. So, we can consider one layer somewhere here with some average value, there also can be considered another layer, this can be considered another layer, this can be considered another layer, this can be considered another layer, like that we can visualize by seeing this how many layers are there in this, and accordingly we can correlate and with different soil properties. Next actually other methods, other geophysical method, one is SPT that I have mentioned, and these other methods are actually, one is geophysical methods, and you can see geophysical is the main, then under that there will be seismic diffraction, cross hole, down hole, up hole, then electrical resistivity, seismic deflection also can be there. So, there are so many, then there can be vane shear test for some soil, then there may be pressure meter test, there are several other tests also there, field test. So, we will discuss by and large this two. Pressure meter we will not be able to discuss here, but these two at least we will try to discuss. So, geophysical method actually, before geophysical method what we were discussing, that cone penetration or CPT whatever, generally SPT if you do, then you have to do boring and then you have to do the test pit, and it will take time and expensive, and give subsurface content only at boring or test points. That means, if I conduct the SPT test at a particular, suppose this is a site, sorry. So, this is the site, suppose this is the site, and I have carried out SPT here, I carried out SPT here, I carried out SPT somewhere here. That means, whatever information I am getting related to this point and this point, and I am considering the average all three is the site condition sometime. So, that is what, that means, we are getting the information for a particular point. So, that is the limitation of this type of SPT and CPT test, whereas geophysical method is quick and less expensive, can cover greater area thoroughly. That means, if I study this one, I can get the entire area how it is, but results are more in qualitative nature. That means, not exactly some range will get, not exact value will get. So, that is the limitation, but it is quite quick and to get the continuous information. So, for that geophysical method is also important, many times we use, and very quickly it can be done, it can be covered in a large area. So, we will discuss one by one some geophysical method, that is you can say first under this again you can see there is a seismic reflection, seismic diffraction, seismic uphole, seismic downhole, seismic crosshole, and electrical resistivity. There are so many methods, and let us discuss one by one. So, seismic deflection is nothing actually. Seismic deflection is just if I know this and I can find out the from here to here travel time, if I know, then I can find out the velocity actually. If I know other details, this distance if I know and all, and this depth you know, then I can find out the velocity. This is sometime to find out the depth of the sea and other thing, this is used, but otherwise in soil most of the time we do seismic diffraction, uphole, downhole and crosshole. So, I will discuss that actually in detail. So, seismic diffraction method. So, in this actually there are number of waves will be coming, and that first arrival time of the P waves are recorded. That is most important in the instrument, that is the arrangement will be there. The P waves first arrive, that will be recorded in the seismogram, and then travel time versus travel distance plot will be done, and from the plot one can obtain thickness of the layers and velocity of waves through each layer, and which is related to the shear modulus and elastic modulus of the soil. So, that means, if I know the velocity and velocity of the particular layer, actually if I know the velocity, that is what V actually rho V s square actually. So, from here actually we can get the shear wave velocity if I know the velocity. So, that seismic diffraction survey as or test, as I have mentioned, that I want to discuss, and you can see the testing method is like this. There will be a explosion or the source where actually will generate waves, and when the waves generates, the waves will be moving in different direction of course, and we can see there will be a number of receivers are kept, and the soil may be stratified, and then what will happen when waves can go in a number of ways. Waves can go directly to reach to this like this, and sometimes waves can strike here and then move with this and then again reflect back and reach to somewhere like this. So, partly reflected and partly reflected. So, this way the travel waves can move this way or wave can move this way like that, and traveling by these two ways, which one is faster, actually that will be recorded. So, you can see that there may be few pickups where straight path, because this test actually will be applicable when V 1 is less than V 2. That means, this layer actually shear wave velocity higher. So, because of that, though this is going this way, but going straight way the lower velocity. So, still if it goes by this way, still it may reach faster here this way, because the velocity here is less. So, that is the way actually. So, number of, if this there will be explosion or source point and there will be receiver, that means there are number of points where actually we are recording the arrival time. So, that means from this point to this point waves are arriving at what time, how much time it is taking, and we will not be able to identify initially whether it has come from this way or it has come from this way. If you plot only, then only we will be able to find out. So, this actually what actually happen. So, if it travel this way direct path, then it will be same material. So, velocity will be distance, or L divided by T will be velocity, and it will be for everyone it will be applicable. So, it will be linear. So, that means up to the receiver where actually it has direct path, it has come faster, that means they will be representing these points, and when there may be some points where this path is coming faster, okay, there also they will also follow linear. Why it is so? Because you can see when the waves are coming from here to here and then traveling this way and then reflecting here. So, this and there are three parts. Okay. So, this and this one part that is traveling with the first material, and this is actually traveling with the second material. Similarly, if it goes from here and then move this way and then this way, and you can see this and this part again traveling through first material and this part is traveling through second material. Now, this and this and this and this are same. Why it is same? Because this reflection angle and refraction angle depends on the material actually by Snell's formula or the Snell's law. So, this and this angle will be same. So, that means this distance and this distance will be same, these two distance will be same and together, and similarly this and this also will be same. So, because of that, when the particular wave is traveling from here to this way and this, here to this way and this. So, these 2 points if I plot travel time versus distance, then also will be linear. Here actually directly linear means here it was y equal to mx form, and this part actually this plus this actually traveling through the first material. So, that will again this plus this traveling with the first material, that will be constant part. So, second line will be equation will be y equal to mx plus c. So, mx plus c, that means travel this distance by this distance divided by velocity whatever time, that is actually becoming the constant. So, this is c. So, that is why this line if I extend, you can see this equation of this line is nothing but y equal to mx plus c, whereas this line is y equal to mx. So, that means, if there is a stratification and if I generate waves and keep number of receiver in front, then some of the waves will be reaching directly to the receiver, some of the waves will go to the second layer, and then some of the partly it will reflected and partly it will be refracted. So, reflection part will reach to the receiver little away, and like that subsequent other receiver also will receive this path also. But while you plot, you will see that your distance versus travel time, this plot will be linear. Initial few records may be linear, that represents that they are coming directly. In another few records may be again linear, but it is linear with a form y equal to m x plus c, that means there is a constant part with m x. So, that means that is again representing another layer. Like that, if I get subsequently another slope, then that will represent third layer. Like that, distance versus travel time, if you plot simply in a graph paper, then by eye estimation we can think, you can imagine, you can visualize that the a bunch of data is representing a straight line. That means, those portion is actually through the particular layer like that. So, that represents slope of this line represents actually inverse of velocity of first layer. Similarly, slope of this line is giving you inverse of velocity of the second layer. So, that is the way actually you have to utilize the refraction method for finding out shear wave velocity. So, next is so that means we will have the source here, and we will keep number of receiver in line, and then the wave actually will try to move different ways actually, that, and our condition is first arrival time to be recorded, and first arrival when they are going directly maybe in few records. So, they will represent one straight line, and next subsequently there may be few records coming through this way faster than direct path, that will represent also another straight line. So, slope of this line will be inverse of velocity of second layer, slope of that line will inverse of velocity of the first layer, and this intersecting point of this two straight line will give you the thickness of the actually some calculation we will see, that is actually to be recorded actually some number L1 suppose, and that L1 will be used to calculate the thickness of the layer. So, I will come to that subsequently. You can see here that V1 is the wave velocity of the layer 1 inverse of the slope of the. So, I can, if I know 2 points, if I suppose if I this is actually if I know these points. So, this is L1 and this is L2. So, L2 minus L1 is distance and T2 minus T1 is the V1. So, distance by time is actually V1, that actually you can find out, but if I want to find out slope of this line. So, this is T and this is T and this is L. If I find out the slope of this line, it is becoming T over L. So, that is why inverse of slope will be velocity. So, inverse of slope of the distance versus travel time plot will be velocity 1 directly. Otherwise, on the line you can fix 2 points and to read the velocity, and those 2 points you read the time. So, difference of velocity divided by difference of time divided by difference of length divided by difference of time gives you velocity 1, or you directly if you plot a graph paper, you just measure the slope and then inverse it, that will give you also directly the velocity of the of that particular layer. And similarly, if the second part of the line, suppose if there is another line something like this, then again you can fix 1 or 2 points, and there also you can find out L1, L2 or whatever number and T2 minus T1, and then you can do there also you can get the velocity. Otherwise, you can again find out the slope of this line, and inverse of that will be velocity of that line, and H1 can be calculated, that is actually that means thickness of the layer will be the half multiplied by V2 minus V1 by V1 plus V2. So, by this formula. So, no, here actually there is something missing. This formula may be wrong. I have to correct. There will be L should be there actually. This L should be coming into this equation. I will correct it later on. So, L is the distance taken from the fastest time. So, that means as I have told you that there is a one part is this and this line and another line is suppose this. So, intersecting point of these two lines, that is actually L. So, that L should come in this calculation, in H1 calculation. So, that I will maybe correct later on. So, this is the way actually we do the correction for we do the by seismic diffraction method, we find out the velocity of the layers, and if you know the velocity of the layer, then actually you can find out the shear wave velocity. There is related shear wave velocity is related to velocity of the this velocity. So, this is the problem actually. Suppose if the data is like this. So, one set of data is given, the distance from the short point, that means as I have mentioned that you have the source somewhere here and you have explored and some velocity waves are generated and then it will move like this. Okay. So, there are receivers and if there is a layer, then it will go like this, it will go like this, then if it is like this, then it will go like this. So, like that. So, number of receivers are there and the distance from the short point 2.5, 5, 7.5, 10, 15, 20, 25, 30 like that is given, and time of first arrival, suppose it is millisecond 11.2, 23.3, these are the things are given. So, by using this you have to find out the velocity of the shear wave velocity in the two layers of the soil, and you have to possibly you have to find out the thickness of the layer. So, this one if you plot now, if I have attempted to plot this one in the Excel and I can show you how it is coming. You can see that the Excel came like this 2 points, and you can see that these are the 4 points by and large a straight line. You can see. Okay. And another thing actually these 3 points and again by and large a straight line. Okay. So, now from here actually that means for calculation of thickness this will be give you L1 and you can find out the slope of this line, either slope of this line or I can find out L2 minus L1 by T2 minus T1, and if I do that then you will get like this, velocity will be something if you do this one for this one. So, if I consider these are all in line, then it will be 5 minus 2.5, that is L2 minus L1 divided by T2 minus T1, that means 23.3 minus 11.2, and that is supposed to be V1. So, if I calculate this will be 5 minus, so it will be 2.5 divided by 23.3 minus 11.2, that gives you 0.2066. It gives you 0.2066 meter per millisecond. So, if I make meter per second, so it will be 206 meter per second. Okay. So, similarly, if I have taken first two, similarly I can take 2 and 3 between, that also you can calculate, And similarly, if I want to find out the slope of this line or velocity of this, then I can take these two readings. So, that is actually if I do that. I want to find out V 2 suppose. For V 2 calculation, I will take suppose these and these 2 points. So, these 2 points basically I have these 2 points, your velocity is 25 minus 20, 25 minus 20, that means 5 divided by your 64.4 minus 57.2, that gives you point, that gives you it will be 25 minus 20 divided by 64.4 minus 57.2. This is actually 57.2. This gives you 0.694 meter per millisecond, and if I convert into meter per second, then it will be 694 meter per second. So, and this is actually by I am assuming this 3 point exactly straight line, and based on that I have calculated the similarly I assume that this all 4 lines are exactly straight line, then I have taken that one and using those I calculate. Otherwise, if you take a plain paper of graph sheet and plot this one, and then you find out the slope of this, find out slope of this slope of this line, slope of this line. So, inverse of this slope, inverse of this slope and inverse of this slope, this is inverse of this slope, this is V 1 and this is inverse of this slope, become V 2, and this will be L 1 and L 1 will be used to calculate H 1 by that formula, and that formula it will be basically it will be L by 2, that is actually L instead of 1 L by 2 multiplied by V 2 minus V 1, V 2 minus V 1 by V 2 plus V 1. So, that means it will be that is 200 this is 206 and 694. So, it will be 694 minus 206 that divided by 694 plus 206, that. So, it become 0.54 under root 0.54, that will be 0.73 multiplied by this distance will be coming something around 11 or so, 11 or 12 it will come. So, your this distance will be multiplied by, if I take 12 and divided by 2. So, that means 4.4. So, this gives you the H 1, that means the thickness of the first layer is around 4.4 meter. So, that means this is the way actually one has to do the calculation. That means, if you get if you generate a disturbance at a particular source point, and if you keep a number of receiver in the same line, then you get the first arrival time recorded, and then you find out the time to arrive first arrival and distance, then plot distance versus travel time, and then we will see the data, then we will see that a bunch of data will be in a straight lines. So, that bunch initial bunch of straight line will be connected by one straight line, subsequently other bunch of data can be connected by a straight line, and then slope inverse of slope of this line will be velocity 1, inverse of slope of this line will be velocity 2. If I get another line also inverse of slope, it will be velocity 3 also. So, that I have not discussed, but if I then two straight line is intersecting at a particular point, that intersecting point to be measured from here and that to be used for calculation of thickness of the first layer. So, that is the way one can do the calculation. Okay, so, maybe then seismic cross hole, this is a method actually. I will just quickly show, this is the ground surface and there will be one borehole will be made, and this will be another borehole will be made, and there will be source here, that means some disturbance will be kept and receiver will be here. So, if I know the distance by recording at different depth, we can find out the velocity. Similar to this, there is a seismic downhole, that means we make a we make a disturbance at a surface. Suppose this is downhole, and in the borehole actually from different location we can receive. So, this will be the receiver, this is the different distance we can find out at what distance from if you know this distance and if you know this distance, then and if I record the travel time from here, actually we get the velocity. Similar to this, we have off hole, actually the off hole is just reverse, that means in the borehole itself we will put disturbance and on the surface we will keep receiver. So, it will go this way, this way, this way, this way, and if I know this distance and if I know this distance, then we can find out the velocity. So, like that there are several seismic methods are available, and then afterwards and of course, another geophysical method is resistivity method. Perhaps I will take this one next class. Okay, I will stop here. Thank you.